But it's by total accident. Maddie was texting us in that group. I go, why didn't you guys just both fire? You said something along the line.
All right.
Oh, thanks, I haven't thought of that. I was like,
So it looks like we're good. Looks like it's working better.
Start your car.
Oh man, it did it again.
Rubbing off the
New Broncos.
That's a good mascot.
They're football team like one state 1 year. So
I was just thinking, like, it's cute.
All right, you guys remember how I moved that window?
Yeah.
Got it? How did I do it?
Wait, what? Didn't you say it worked?
So like, if you're locked in one, you forward it.
I knew
Yeah, it's off screen. So let's check it out. Windows.
It's like, bro, put Rain-X on it. It'll never freeze again. It's like, Matt, that wouldn't work.
Move window short. F. No.
Hold
down Alt key, space bar, and then F. Alt key, space bar. Oh, there it is.
You know it.
Probably didn't realize until we talked to Ray and probably wasn't good for.
We don't have it.
Yeah, mine's for
Literally the first time I've ever heard it.
Our studio.
Winter wiper bar. Never heard of it.
No, mine's
Okay.
It's just the normal shit you put in your windshield wiper. Tequila? Yes, that would actually probably work. Yeah, I know.
Expensive way.
Yeah, I know. Now if you get the cheap stuff from
I
Mexico.
only use whatever the silver label is. You know? I know.
Yeah, you get the cheap stuff from Mexico. It's 5 gallons.
All right. Finally. We're gonna see. IT will show up and I'll just tell them what I did and say I'll just keep doing this until it works. So Apple was our practice problem. Did you have any problems going through it?
No.
Let me open it. There's Apple. Okay, strings as factors. Import, so fertilizer and diameter. All right, so our variables, fertilizer, and we have diameter, right? So which one is our dependent variable? Which one's our independent variable? Which one? Fertilizer?
Independent.
All right. And the other one's dependent?
Yep.
All right, so what's our question?
This diameter is buried.
All right, so does diameter vary between the fertilizer treatments? What's our null hypothesis?
The same.
Yep. So all means equal, alternate.
They're different. Not equal.
All right, so at least one mean differs. So what kind of test do we want to run? ANOVA, right? So that's our target test.
Yeah.
That'll address our question. We had this overall question. We have our null and alternate hypotheses. Now we know what test we want to run to try to get it working properly, right? So targets ANOVA, we have to check our assumptions first, right? So first up is normality. How do we run normality? QQ plots, right? So QQ plot, we can do diameter as a function of fertilizer. Where's the function of fertilizer? Date is Apple. And first thing I gotta do is make sure car package is loaded, because I know it's not. We're gonna run this. I get these plots, which I can see it on my screen. What do you think?
good.
Yeah, they look pretty good. This might be the only spot, N and P. So if we wanted to, we can run Fligner clean.
I'm having a hard time getting my data center action.
All right.
Hello.
Hello. Yep. How are you doing? So I managed to get it.
Okay.
But I had to swap the cables. So it's just not ultimately. We had this one used to be here. Once I put both of these HDMI plugs on this one card, then I had access to the other one. Yep. Everything works good. So I don't know why it worked. I logged out and logged back in and made sure everything was set up as it was last week. When I met with and it worked on Wednesday. But then it wasn't working. So that's what I did. Just to get it. Okay. Yeah.
Do you guys have any more?
Yeah, it's just like add a note. I don't know if someone else was on here, but it was I couldn't add whatever plug was on. I guess that's the NVIDIA card. It just wasn't accessed.
Okay.
I think your bosses might know about it because we ran into that in the fall.
So I did that for so my thought process.
My boss. Yeah. Yeah. So I did that. I see him at the gym when I was going to the gym. Yeah, it works now.
If you have any more issues with it, definitely call the service center.
Okay.
Classic progress, so.
Yep. Oh yeah, no. Thanks for coming.
Yeah.
Much appreciated.
All right, so we got did you get it?
Yeah, but it's still not showing up in my global environment. It's weird. So like some of them show up and then some of them don't. And I've done it where I tried to re-import it again. And then I even went and tried to download like for the but it just keeps hacks. It says it's got the P code, it's not in the environment, and it doesn't work for a while. Like it'll work for since.
Oh, I know why. Yes, scroll up and see where you read in your data set. We'll see. Let me know which ones don't work. All right, so IT came out quickly. That was awesome. That's the last guy commented. It seemed like you're pretty good with computers. That you already knew the issues. Still working on it. Yeah, there was some higher ups that came on. They had younger people working behind, and everyone else was just supervising.
What did they say the solution was?
So we figured out ultimately that it was the video card. It wasn't playing nice with the NVIDIA video cards. So I don't know what they did on that room down there. I know they were swapping out cards, and it's a known problem on the software. I've got them all on one card, so it works. All right, so yeah, QQ plots look pretty good. If you wanted to be extra cautious, you could try Fligner clean. Right? And that's what I could do, not because I'm really concerned about it, but just to kind of demonstrate that when we run the Fligner clean, right, diameter is a function of fertilizer. You're going to get a p-value that's 0.3144. You're going to get a fairly large p-value. So I'm not worried about normality. I'm not worried about unequal variance. If this p-value was, let's say, 0.08, then we've got a concern because maybe our test isn't powerful enough to actually detect that unequal variances. But here, without a doubt, we can detect it. Or it's equal variance. It's homoscedasticity. General rule is if it's around that 0.08, 0.07, 0.06, that's the level where it's like we might not have enough power. Some people would say go all the way up to 0.1. I would only do that if we have small sample sizes. As our sample sizes increase, we'll be able to detect it. So right now, Flickner Clean says that there's equal variance. Even Brown Forsyth would tell me it's equal variance. So I think we're going to go with it. So we run our ANOVA. There is shortcuts to do it. I'm just going to make my model. So it's a linear model. We are fitting diameter as a function of fertilizer. Create that. And then we're going to generate our ANOVA table to look at that. So I'm just going to run the chunk. And I get a very small p-value. So we have to report our test statistic. That's our f value. We have to report our degrees of freedom, and we need both of them. So it's 2, 182, and our p-value. So are the means equal? No. No, they're not equal. So next step now is do our post hoc test. So all assumptions are met, and we're interested in, okay, well, which one's different? So I'm just going to run a 2-piece, all pairwise comparisons, and we run it by doing 2-key HSD on the AOV of our model, so that ANOVA information on our model, and we get this output. So these are telling me the comparisons. So right now I know that if we have P only, phosphorus only, and nitrogen only supplements, we don't see a difference. We get a difference if we compare N only versus the combination, and if we compare P only with the combination. So the question is, how do we kind of summarize it? Well, for summarizing, I'm just going to take a look at the plot. Take a look at the plot. So I can see, just based on the median comparison, I think what we're saying is we get increased diameter when we supplement both nitrogen and phosphorus. And if we only supplement one, we're not getting much change at all, or we don't see a difference. So that's a pretty simple explanation. They didn't have to go through every single pairwise comparison and say, well, it's no difference between these two, it's different between these two, it's different between these two. I didn't have to say that. I could just say nitrogen and phosphorus together increased our final diameters, and that was a significant difference. So you can see, as you start presenting your data at presentations or in papers or in theses that should be rapidly showing up on my desk soon. I think a couple people are in here, right?
Yeah.
You're getting close?
Yeah.
Cameron should be close, right? Yeah, we got a couple people. Well, I feel like I'm on everyone's hiding.
We're on. We're working on it. Yeah. Really hard.
Yeah, so remember, brevity is the soul of wit, all right? Think about how do we best relay the information, the main points of our data, in as few words as possible. And I think with this, I would just say highest diameter was observed when we supplement both nutrients. Any questions on this? Not too bad. All right. Let us open up the next one. So the next one's going to be a little bit harder. A little bit harder. I'm glad I got this done. Move R out of the way. So we are going to that issue when we want to run the ANOVA, we start checking our assumptions, and then we see, crud, we violated an assumption, or we violated both assumptions. What do we do? How do we analyze our data? How do we continue analyzing our data? This is probably the thing that's most important overall, and it's something that not everyone does. So, leaving here and saying, sorry, I hit pause. So leaving here, with the understanding that, assumptions are important. And we can't just run the test and violate our assumption and then say, oops, we can't do anything. That's not what we want to teach. We want to take this approach and say, if we do violate our assumptions, how do we respond? So this is what we're going to be working on. We've got our assumptions of ANOVA. Data are random and independent. All right, that's another topic, and maybe we get there. Probably not with our last 2 weeks. All right, but if you have that situation, and if I know you have that situation when you come talk to me about analyzing your data or being on the committee, we can approach it there, and I can show you how to go about dealing with the issue. The two that we're going to focus on is the normal distribution. So you have to be normally distributed within each group. And then the second one is data are homoscedastic. The most important one is this homoscedasticity because we are using the variances within groups versus between groups to determine if the means are actually different. All right? So if our variances are unequal, that really throws a wrench into our analysis. So much so that our F that we would get in those cases no longer follows this F distribution. And if it doesn't follow the F distribution, then we can't use our statistical tables, we can't use the PF function in R, which is what our ANOVA does, to generate our p-values. All right, so if our assumptions are met, we run the test, we have faith in our p-values. If we violate the assumptions when we run the test, we're not going to have faith in our p-values at all, and we shouldn't. The exception is normality. ANOVA is robust against that violation, so typically, if you violated normality, you can proceed with the test and have a good amount of faith that you're good. So the question becomes, what happens if we violate? What do we do then? So I think what I've done is created like a brief summary that you have at the start. So assumption one, if our data are, violate this random and independence, then we're going to be forced to use some sort of mixed effects model. It's built into R. Right? They have a mixed effects models package. Not terribly difficult to run. There are some catches with that, but if we get there, we get there. Assumption number two, if we violate normality. Fortunately, as I said, ANOVA is robust against this violation, so we can often ignore it and proceed as usual. Now, we can proceed anytime, but there are certain times where it's like, yeah, definitely we can proceed, no problem at all. And those situations are if we have large sample sizes in each group, that normality assumption has less of an influence on the p-value. If we have large sample sizes and our sample sizes per group are very similar, if they're exact, that's great, but usually they're not, so they should be close. Let's say we had 5 groups. If we had between 90 and 110 samples in each group, I'm going to be less concerned about that normality assumption. ANOVA is robust against that. Right? But if we have if we have 3 out of our 5 groups at that 90 to 110 range, and then we have 2 groups that are like 15 or 20, we've got a problem. We've got a sample size issue in our groups. And then also, I'm going to say if the non-normality isn't too drastic, you can proceed. And what do I mean by that? There are certain data types that are non-normal just in their nature. Those, yeah, don't proceed with ANOVA. Normally on those, a transformation can take care of it. So if you transform the data, then usually you can perform your ANOVA. But if you don't, if this is completely new to you, you weren't expecting that skew, then you probably want to run a randomization test. Assumption number 3 is that equal variance assumption. This is probably the one that I like violating the most because our solution is to run a Welch's ANOVA. It's an adjustment. Basically an adjustment to our degrees of freedom, which then adjusts our p-value, which makes the test a lot better. And it's really easy to run. That's why I say it's very simple. We don't have to run randomization tests. We run our Welch's ANOVA. And then in our t-test, we can run pairwise t.test, which also has a Welch's adjustment. So it just makes analysis a whole lot easier than the other option, which is to run a randomization test. What happens if we violate both normality and homoscedasticity? We're running randomization tests. That's about all we know. What happens if we violate all three? Well, you're going to be running like a mixed effects general model. You're going to be doing randomization and other alternative model selections. All right, so we have a working data set first, which is oaks.csv. So in this data set, we measured the diameter at 4 different sites. Question is, are the oak trees similarly sized across all the sites? So download them, make a figure, take a look at it, and then go ahead and check our assumptions, because again, you're going to see our target is an ANOVA. Check our assumptions and see what they look like. Do that. It's the same thing. Matt, have you logged out and logged back in, or closed R and then reopen it? Is it doing the same thing?
No, I haven't tried those.
I would just close RStudio, make sure it's saved.
Yeah.
Then close RStudio and then open it and see if that gets your environment back.
It honestly seems to be working. So
Except
far.
the
I
environment.
just can't see the environment.
Okay.
So I'm just doing view.
Okay, that can work. I'm not capitalizing my voice. Why it's connected, the diameter. I would say that they do. process. All right, so did you get it?
Good.
So here's my plot. I look at it, and again, we look at it just to kind of get an idea of what to expect. I can see that we have changes, differences. These are medians, but I think the mean's going to be the same way. But notice the spread of our data. I think that's kind of the important thing. So on these plots, if we are non-normal, I should say, on these plots, if we are normally distributed, our mean equals the median. And on the plots, then, our medians would be in the middle of the boxes. All right, so here, yeah, for the most part, it looks pretty good. They look to be in the middle of the boxes. All right. If we have equal variances, then our interquartile ranges should be pretty similar. We could somewhat rely on the whiskers, but the whiskers go out to either 1.5 times the interquartile range or the maximum and minimum values. Sometimes you can have that low probability data point that's outside of our 95% confidence envelope, but it's at the very ends. That would be these points. So the more reliable measure is the width of these boxes. And you can see there, that's a pretty wide one, that's a pretty narrow one. So I look at this and I'm thinking, okay, I'm not sure if my equal variance assumption is going to be met. But I can't start there, I have to start at the normality assumption, because that informs me as to what kind of test I'm running to check the equal variance. So I can see, based on this plot, that it looks like all of my points are following that line. They're all in that 95% confidence interval, or at least nearly all of them. So yeah, I think these are normally distributed. But so I run the Brown-Forsyth test, and I get this output. So what's my conclusion?
That it's normally distributed, but that it's non-homoscedastic.
Yeah, so they appear to be normally distributed, but they're heteroscedastic. All right, variances are not equal. So what do? Well, we can't run ANOVA, because if we run ANOVA, our p-value is going to be off. All right, our p-value is going to be wrong, and the reason it's wrong is that F statistic no longer follows an F distribution. So our two options: Welch's ANOVA, or a permutational ANOVA, which is a randomization test. All right, so Welch's ANOVA is going to be the preferred method. We access it using the function oneway.test. So if you ever looked up how to run ANOVA in R, there's a good chance that you'll find people using this oneway.test. All right, and with the oneway.test, they set it up as a formula in the data, and they'd say var.equals t to run the ANOVA, which works. However, we're going to be moving on and using these linear models. So I think it's best just to go ahead and create the linear model and then use ANOVA for the regular ANOVA test. But we don't have access to Welch's correction. This gives us Welch's correction. So the things we change, we write the formula. Dependent variable as a function of the independent variable. Right? We give it the data frame where we find those variables, and then we say var.equals f. If we get a significant p-value, so if we find that the means are different, then what we would have to run is pairwise.t.test. Why pairwise.t.test? Well, Tukey's requires equal variances, so we can't run that. But there is a Welch's adjustment for the t-test. So we can access it using t.test, our formula, our data, with var.equals f to say that don't assume equal variances. But the catch with this t-test, if you try to run it on your data frame, or on our data oak data, it's going to fail. It's going to say that you need exactly 2 levels, because the t-test is only comparing 2 means. So what we would have to do is use subsets, and basically run a t-test on our subsets of the data where it only has our 2 groups. So we have to run each of these t-tests, each pairwise comparison, save the p-value, and then adjust our p-value to correct for that inflated type 1 error. I'll show you a shortcut for this one too. Our alternate, one that I'd say it's not my recommendation, but we could do it, and that's running a permutational ANOVA. So with a permutational ANOVA, what we're going to do is we calculate our F statistic from our ANOVA. We save that value. That's our observed value. And then what we're going to do is shuffle our classification variable, shuffle our independent variable. So by shuffling it, we kind of take that independent approach. So again, what we've assumed with our null hypothesis is that each of our groups is just a random sample in the same population. All right, that was our assumption. So based on that assumption, we calculated an observed value, observed F statistic. With our permutational ANOVA, what we're actually going to do is eliminate our actual grouping, shuffle up our classification so that we really are getting a random sample out of our own data set. So by doing the shuffle and calculating our F statistic each single time, what we are generating is a null distribution of our F statistic. And then what we do is compare our observed to what the randomized data set looks like. How extreme is it? And I'll show you how to do it. We'll kind of walk through it again and give you a little bit more details on what's happening. Now, if we get a significant p-value out of this, then what we have to do is permutational pairwise t-test. So again, just a series of randomization tests, save our p-value, and then adjust it at the end. This takes a lot more time than this, and that's why it's preferred. All right. So I'm going to add a note down here. ANOVA is robust against violations of normality. All right. It is robust against that. ANOVA is robust. ANOVA is robust against unequal variances if our sample sizes are equal. So if we go back and we have 50 individuals in each of our 4 or 5 groups and we have unequal variances, we could probably get away with running an ANOVA, but as a word of caution, I wouldn't do that. I'd still run Welch's. The consequence of Welch's is that we lose a little bit of power. All right, we lose a little bit of power, but I think it's a little bit better than try to explain to the reviewer how it's robust and then finding out, digging into all of the randomization papers that actually investigated that issue. All right, so we ran unequal variance. This is how I would run it with our Oaks data set. Pretty simple. Oneway.test, my formula, bar.equal equals F. We have our test statistic. There's our F. We've got our 2 degrees of freedom, and we have our p-value. Now, when you report the Welch's, note the degrees of freedom here for the denominator. It's not a whole number. So when you report on the Welch's, I would report what R gives you and let the editor tell you otherwise. But in this case, if a reader gets to it and says, oh, the degrees of freedom is 119.76, you must have used some sort of adjustment, probably Welch's, to correct your p-value. And if you didn't say it, they would call you out at that time. But if you left it off, if you rounded to 120, it's going to, and you didn't say you were using Welch's, I know as a reviewer, I'd look at it and say, well, I assume you're running a regular ANOVA, but you didn't. All right, so on this data set, the means differ, but we don't know which means are different. So our post hoc test is going to be pairwise Welch's t-test. That's what it's going to run. Now, I gave you the preview. Said one way is to do all of our subsets. Make subsets, run our Welch's t-test on it, save the p-value, and adjust it. That's option 1. I'm going to show you how to do that. Option 2 is to let R do everything for us. Make all the subsets, generate the p-values, and the adjusted p-values and everything. And I'm going to show you how to do that one as well. So, option 1 is going to be the subsets. And the reason I'm introducing the subsets here is because as we build more complex models, there will be times where we have to create our own subsets to do the post hoc test. There are no shortcuts in R. So if you learn how to do it now, you can demonstrate that making your subsets gives you the same answers as when R does it for us. You're going to feel a lot more confident later on in this course. So how do we create our subsets? We're going to use the subset function. All right, so the subset function takes a data frame, and it's going to return a data frame. All right, so with our data frame, what we're going to do is specify the variable that we are selecting on. All right, so the data is our data frame. The var in this case is the variable name in that data frame that we're selecting on. So for us, it's going to be site. All right, that's what we're going to select on. And then we're setting up a logical comparison. We're doing double equal sign to say we want to pull out all of those individuals where that variable matches some condition. And that condition has to be exactly how it appears in our data frame. Then we're going to use a pipe symbol, that's the OR symbol, because we want to select where our variable matches this one condition or it matches a second condition. So what it'll then do is it'll take a data frame that has your 4 sites in it, or 5 sites, 4 sites in it, and it'll pull out 2 of the sites and return that data frame so it only has 2 sites. So as an example, this is Oaks, where we pull out site A and site B. That's our example code. So I'm going to go through so subsetting data. We're going to demonstrate it. So, what's that? Yep. Subset. So we're going to subset on our Oaks data frame. The variable that we're selecting on is site. Yeah. Shift. See, man, you guys like lost out on like making text figures, like in a notepad document where you have to use slashes, the pipe symbols, brackets, parentheses. Some people have way too much time. All right, so our site names are A and B.
Do you need 2 equal signs?
Yes. So those on the video. So here's our subset. This, so 2 equal signs. Oops. Do this. We'll do an arrow. 2 equal signs means a logical comparison equal to. All right. 1 equal sign is the same as our arrow. All right. So if you did site equals A, there's a possibility that you will overwrite your site variable with the A, with the letter A. I don't think so. I think since it's in the subset function, it protects you from that, but that's what it does. So 1 equal sign is the same. All right. 2 equal sign. Pipe symbol. So our pipe symbol is the key above enter or return. I guess Mac did that move to enter, or is Mac still return?
Return.
It's return. See, it's ridiculous. Why? Actually, hold on. We're gonna side note on that. Why was it return instead of enter?
It was for typewriters, right? Shoot back? No, that's not right either. Because you know.
I actually think it was a dispute. There was a reason why they're not the same. And I think it was a dispute between the people. Between
Gates and Jobs?
Yeah, I think so. There's an interesting story tied to that. Anyways, yeah, pipe symbol is a key above the enter or the return key. Most of the time, you have to use the shift key to access it. All right, so the pipe symbol is a key. This is the logical OR. So it's either site A or site B. So using this code, when I run it, you're going to see that everything that I have, all of the output, move this down just a little bit. As I move through the pages, it's only A and B. That's all that's there. All right, so what I could do is pass this entire subset as the data inside of our t.test function. We can do that, or we can create a new data set where it's only those two values. So I can say oaks.ab and save it. So then now oaks.ab becomes the new data frame that I would use in my t.test function. All right? So that's one way we can do it, and that's probably the way that I normally do it. That way I can make all my subsets at once and then run all my t-tests at once using those same data sets. But that's not the only way. Because we know that subset returns a data frame, what we can do then is pass this entire thing to our t.test function. So t.test, diameter is a function of oaks, where our data is the subset function. And then var.equal equals f. And space after that. So our data frame isn't that oaks.ab, it could have been. Or I do data is equal to the subset of oaks, where we're looking at site is A or site is B. And now that gives me my two groups in that data frame. It now allows the t-test to run. So if I run this, you'll see that it doesn't work because
you have diameter of
diameter of site. Yep. Now it works. Now we get our p-value. Everything works as it should. And it's right. It tells me the mean in group A, the mean in group B. Gives me my t-value, my degrees of freedom p-value. Do we report this p-value?
Yes. No.
Not yet. We haven't adjusted p-values yet. We're going to save these. All right, so there's ways to do this subset. All right, so what we're going to do, get to that, is I've run one. All right, and what I'm going to do is, this is p-value adjustment. All right, I'm going to make a p-value vector. So creating a vector is our object name. I typically call it p-val. And then the arrow, because we're making that object, and we're going to pass it a vector. So C, and then in parentheses, we're going to combine all of these into a vector. So what I'm going to do is combine our p-values. So that is the first one that we have that we need to report. All right, that's the first one that we need to report. So now I need to run a series of my tests, making sure that I cover all pairwise comparisons. Which are 6. So what I've done, just out of everything that I've been doing. Hey, Rebecca emailed. I wonder if she's watching.
Stop watching.
She's like,
5 minutes.
Yeah. Well, I waited 10 minutes. We had 6 sites, A and B. So I knew the first site, the first function worked. So now I copied and pasted that. So I can just use my arrow keys to kind of update what I'm comparing. So this will be E. So we got A versus B, A versus C, A versus D. B versus C, B versus D, and then C versus D. Now I can run the entire chunk, and I can get this really long output. And that's fine. That can work. But I'm going to go back and run one line at a time by using my control enter, or I think it's map key, command key enter. And also you can run it as run just the current line up top. Run the current line. and it should also just run the line. So if I run the second one, I have my output, and I can see it and I can access the next chunk because I need the p-value. So now it's a p-value 1.348 e to the negative 12, comma. All right, so that was number 2. Number 3, 0.1729. Number 4, 1.091 e to the negative 9. Let's see here, 5. 0.00099973. And our last one, 0.000131. I've gone through and made my vector of all of the p-values for the 6 pairwise Welch's t-test that we ran. All right. And again, it works. If I run the chunk, it works. I just have to keep scrolling up and down. And if I do that, then I make it a little bit easier and just highlight the output, copy it, and paste it, and just go one by one. Just making sure that I have all 6 comparisons in that p-val vector. All right. So now what we need to do is adjust our p-values. And the function is actually pretty easy. It's p.adjust. But we have to give it the vector of the p-values. That's what it's asking for. So based on how many p-values are in that vector, that tells R how to actually perform that adjustment. The 2 adjustment methods that we can use is either Holm or Bonferroni. All right, the Holm adjustment, I like it a little bit better. It has a little bit more power, and that's why I recommend it. But you're going to see a lot of people use Bonferroni. It's well known, but it's a little bit more conservative. So you're going to be a little bit more likely to find the differences with Holm than you will with Bonferroni. Just pick one and be consistent in your paper or publication. That's all I can say. All right. So we're going to use the p.adjust adjust for our p-value. All right. We're going to specify the method, and then we get the output of all of our adjusted p-values, and it's these p-values that get reported on our paper. And I had already mentioned with the 2 keys, usually you want to acknowledge the adjustments. So when we report these p-values, we're going to use p and then adj to emphasize the adjusted p-value, or we would actually say these are the adjusted p-values. All right. So we've already done the Welch's t-test. I kind of was stepping you through how to do it. So we have our p-values in our vector. Let's adjust it. P.adjust, our vector is this p-val that I created. And then our method is either Holm or we can do Bonferroni. Again, with R, it does work if you can abbreviate it. So as long as you're using letters that safely distinguish which method, it'll work. So BONF for Bonferroni will work. Holm works, but you can't use H because there's a couple other tests that begin with H. So when I run this, creates a vector, reports all the outputs, and you can see they output in the same order. You can see the adjustments that are made and how they changed. This didn't change, and that is how Holm works. It kind of looks at the highest p-value and then scales everything based on that. So the highest one stayed the same, but everything else increased a little bit. Now you're going to have to work through like the -1s, -2s, -3s, kind of move your decimal places, but that's what you can do. So out of here, I know that we did our comparisons of A versus B, and then A versus C, A versus D, B versus C, B versus D, and then C versus D. So just kind of systematic comparison. So if that's the order, then I look here. So 1.37 times 10 to the negative 2 is 0.013, 0.014. So that's less than 0.05. A and B are different. Negative 12, different. Negative 1, that's 0.17. So that comparison A versus D, that's not significant. Negative 9, significant. Negative 3, significant. So 3.003 is that p-value. And then negative 4 is 0.0005. So the only one that's not different is that A to D comparison. All other comparisons are significant. Questions on that? You're gonna have a lot of practice with subsets. All right. The alternate method, so let R do it for us. And when we're running a one-way ANOVA, this is probably preferred. Say it saves you time. I should say that it saves you time. All right. So the function is pairwise.t.test. And that function will generate all pairwise comparisons for you. All right, it'll do all of the subsetting for you. And then once we have those subsetted data sets that it has generated for you, it will run the t-test. All right. There is a trick though. So we can't write formulas. This doesn't work with a formula. It doesn't work with a formula. We actually have to give it the vectors, our independent variable vector, and our dependent variable vector, which means we're going to have to use the data $ variable format. Now, the thing that I don't necessarily like is I feel like this is out of order, because we have to give our dependent variable first, we have to give the y variable first, and then we have to give our x variable. Now you can reverse it as long as you say x equals a variable or y equals a variable, you can reverse it. But if you don't do x equals or y equals, then you have to make sure that our dependent variable goes first and then our grouping variable. And I understand why they do that, because a t.test function takes a single variable and you're going to give it that dependent variable, that measurement variable. All right, p.adjust.method is the same. p.adjust.method equals bond or home. The next two are the important ones for this test. Pool.st equals f. One of the ways in which a t-test can work is that it takes pooled variance. And what we're saying is we don't want to do that. Instead, every time we run the test, we want to calculate each comparison's pooled standard deviation. All right? The specifics, not so much, but know that it's pool.st must be false. And then to get our Welch's t-test aspect of it, we pass it bar.equal equals f. When we do this and we say p.adjust.method equals home, we should get the same p-values that we calculated ourselves, doing all of those pairwise t-tests. All right? So go ahead and try it. See if you get the same p-values. Did you?
Yes. Yeah, almost pretty much exactly the same there. They didn't use the E format. Just gave you. In undergrad.
No.
You just made a few all those sorts of.
I did.
Maniacally laughing.
Rebecca emailed me, so she was having issues with car package. So hopefully she'll get it.
I can't get mine to work.
Your car, what?
No, the pairwise.
Pairwise.t.test.
Yeah. I don't know where. You get yours to work?
Yeah.
Nope. What order do we have to put it in? Okay. Is it? Is that Y in our formula? So what you can do to help make it work, that's our X, that's our grouping variable, that's our independent variable is going to be the X, the Y is going to be the independent.
Okay.
So reverse it.
So you p.adjust our method, what, do you say equal or just straight up function?
Equals.
I did mine.
p.adjust.
Okay, mine red.
It would count across, but it independent of.
Right, mine red.
Always bothers me. That order.
I know.
Always.
It didn't fit in my brain.
Always.
But I can barely throw my name on
All right, so did it work?
it. I did.
So, just gonna run this. Pairwise.t.test. Oak, $diameter, that's our Y. Oak, $site, that's our grouping variable. p.adjust method is home. Pool.st equals false, and then bar dot, oops, bar dot equal. Why I couldn't? Why bar dot equal didn't work with the autocomplete? There it is. So, what you can see now, this doesn't give us the negative, the 10 to the negatives or whatever, but we said 0.137 e to the negative 2 is 0.0137. 0.0137. That's the same. 8.1 e to the 12, 8.1 e to the 12. 0.17, 0.17. Everything's the same. So both methods will arrive at the same answer. Both methods gives us the adjusted p-value. Which one's probably easier to use? This one. Definitely with the one-way ANOVA. All right? Definitely with the one-way ANOVA. All right. All right, so yeah, Rebecca's watching. I emailed. I am just going to demonstrate your car package is not being loaded because you had parentheses, you had quotes around it. So whenever you type in the package, the quotes indicate a text string that we're looking for, so we don't need that. When R sees the library package, it's going to see whatever you write next as being the package that it looks for. So yeah, take out the quotes, and it should work. And if it doesn't work, then check under your packages just to make sure that car is listed. So I've got mine listed there. So I know we're on a delay. Hopefully in 5 seconds, we'll get it. All right, questions? All right, so it's 6:12. I know we started late. But go ahead and kind of mull this over, think about it, review, start keeping your summaries. What we'll do next is the normality. So one of the ways in which we can often fix some of our problems is with transformation. That used to be like one of the only ways to approach it. And it's a pretty decent way to approach it. It's something that I mess around with before I start choosing some of the other tests. However, with the ease of running these randomization tests on R, oftentimes I don't even bother. I just say, you know what, I'm not going to spend 5-10 minutes doing transformations and rechecking all my assumptions. I'm just going to run my randomization test. But I'm going to show you how to do some of these transformations or at least how you can do it to double check your assumptions. And if you fix normality and still have equal variance, great, use transformation. All right, so Rebecca says now that she's doing it, she's not getting an error. Hopefully, let's say, so now she didn't get an error, that should have fixed it. Let's see if the QQ plot function will work. And does she, you guys have her contact information, right?
Yeah.
So if she needs some help, you know, just we can answer. Yeah, I think this works. All right, so yeah, we'll call it quits here. If you have questions, please email me. I think our test was supposed to be this week. Yeah, it's not. We're gonna finish this.
It was last week. Yeah.
Yeah.
It was supposed to last week.
We lost 2 weeks. We lost 2 weeks. So we're gonna finish this. We're gonna finish this ANOVA, and then our exam will be like the ANOVA stuff, like all of it, checking the assumptions, you know, doing the correct test based on what we find out from the assumptions, and everything. And that'll be in 2 parts. So here's a QQ plot for Apple. Copy that and get that in the chat. So yeah, we'll get it together. It'll be in 2 parts. We'll have like a closed book part. Make sure you know, like, review things like what do you have to report. You know, the assumptions. Those are things that I don't really expect you to go back and look up. Those are things that you should know. You should be able to look at your data types and be able to specify, yeah, this is a continuous or discrete variable. This is a categorical and nominal variable. This is my independent variable. This is my dependent variable. This is, you know, with this data set, this is probably the graph that I should make and so forth. All right, all that stuff should be off the top of your head. But when it comes to the R stuff, you'll get the data sets and I'll tell you, do this, do that. That we're just kind of confirming, you know how to do the QQ plots and assess the normality. You know how to do your Fligner-Killeen or Brown-Forsyth and interpret those results. You know how to run an ANOVA, you know how to run Welch's or permutation tests and so forth. That take-home part will take time. All right, so don't think you're gonna sit down and knock it out in an hour. Probably takes me about 30 to 45 minutes just to do the key. Yeah, right? Right? Big part of that is a randomization test. All right, so yeah, we'll do that. But again, I think we'll have like the take-home part go live, and then you'll probably have 2 days. One or like not like go live in the morning and it's due in the afternoon. You'll have a couple days to do it to get it out of the way. All right, so if on that take-home stuff, if you run into errors, right, or like what Rebecca had with the car loading the car package, if you run into errors, you can email me and you can get help, because I don't want the errors to prevent you from continuing on with the rest of the exam. All right, all right. One more week. Okay, second week. Guys, have a good one. Hopefully you're feeling better, Rebecca.